Algebra 2. This is 724 day 1, and today we're going to be dividing radical expressions. So this is a topic that's kind of tricky and has a lot of details or finer points, some small processes that we definitely need to practice. So we're actually going to be in it for 2 lessons, so today and then the next lesson. So by the end of this, you should be able to divide radical expressions that have the same index and then simplify expressions that have radicals in the denominator. So the goal is to always get your radical out of the denominator. Your fraction will be completely simplified when you don't have any radicals in your denominator. So we have this thing called the quotient property of radicals. And that's something that's going to help us out with to start. And so what that says is that if you have some fraction, we could call this a divided by b, and you're taking the nth root of that, is that you could rewrite this as the nth root of a over the nth root of b. So, and you can go back and forth between the two. So what we're saying is if you have a root of one whole fraction, you can divide that up so your numerator and denominator are their own roots, and then you can simplify your numerator and denominator separately. So we'll see a few examples where there will be some cases where it's easier to start off in this format, and then there will be some cases where it's easier to start off in this format. Okay, so the nice thing about this is we can go back and forth between the two, depending on whichever one is most convenient. So if we take a look at our first example, let's see, we have to simplify. We have the cube root of the fraction, let's see, we've got 81 over 81 times x to the 5th over y to the 6th. Okay, now this is something that we could actually simplify. It may be easier to divide these up with separate radicals. So what I could do is I could say the cube root of 81 x to the 5th up top all by itself over the cube root of y to the 6th. Okay, so the cube root of 81, well, the largest perfect cube inside of 81 is going to be 27. Excuse me. So we can take that 81 and break it into 27 times 3, and then we have x to the 5th. And then the cube root of y to the 6th, that's really easy. That's just going to be y squared. Alright, so then the cube root of 27 is going to be 3, and then we've got our radical, and then we'll have on the inside, well, we can't take the cube root of this 3, so we'll have to keep that on the inside. And then the cube root of this x to the 5th, well, we can do that by kind of going off to the side, and for x, we would take our exponent on the inside of 5, we would divide that by our root of 3 on the outside, and we get 1 remainder 2. So then, that means that I have an x to the 1 on the outside and an x squared on the inside. Alright, and then this is all over y squared. So, this is as nice as you can go. We're done, and because if you look at this, we got our radical out of the denominator. So this is one example of a case where it's easier to break it up into separate radicals and then simplify them separately. Okay, now number 2 is something different. So for number 2 in your examples, you have the square root of 5a to the 4th, b to the 7th, c squared, and this is all over the square root of a b cubed c. So in this case, it would be easier to have this as one fraction and simplify it as one fraction and then take our root. So I'm going to rewrite this as 5a to the 4th, b to the 7th, c squared, all over ab cubed c. So we turned it into one fraction under one radical. So now we can go ahead and try to simplify some stuff. So between the a's, well, this a down below would disappear, and then this a to the fourth would turn into an a cubed, and then between the b's, this b cubed would disappear, and this b to the seventh would turn into a b to the fourth, and then between the c's, this c would disappear, and this c squared, well, that exponent would disappear, and it would turn into just c. So now what you have is the square root of 5 a cubed b to the fourth c. Okay, so the square root of 5, we have to keep that on the inside. To do the square root of a cubed, well, we would take that 3, this exponent of 3 right here, and we could divide that by a root of 2, which gives us 1 remainder 1. So then that means that we have 1a on the outside. To take the square root of b to the fourth, we could divide that exponent of 4 by 2, so we get a b squared on the outside. And then c to the 1, we can't do anything with that, so we'll leave that inside the radical. So here is your answer to that second example, and that's it. So this was a case of a problem where it was easier to have it as one fraction. And you see, when we simplified it, the denominator got nice and simple, and the whole thing canceled, and then we were just taking the radical of something that we were used to dealing with from the beginning of chapter 7. Okay, so ab squared, and then the square root of 5c, and so you get this as your answer, no fraction involved. Alright, so the next thing that we want to talk about are, well, how do you get radical expressions in simplest form, or how do you know they're in simplest form? They're going to be in simplest form when you don't have any exponents on the inside that are greater than their radical, and so we learned how to take those out at the beginning of the chapter. There's no fraction underneath the radical sign, which is something we just talked about, and then there's no radical in the denominator. Okay, and so how do we get those radicals out of the denominator? Well, to get rid of them, you're just going to multiply by the same square root, or in some cases, if you have a cube root, you'll multiply by that cube root squared. So we'll go through some of these examples here. So for number 1, we have to simplify 2 over the square root of x. Okay, so the problem here is our root x in the denominator. So to get rid of that, we would multiply it by root x, right? Because if I do root x times root x, the square roots will cancel, and I'll just have x, okay? Now, if we take this fraction and multiply it by something, we might end up changing it, but if we multiply it by 1, we don't change it. So what we want to do is, if you multiply by the same thing in the numerator and the denominator, you're multiplying by 1, so then you're not changing it, okay? So we want it to be the same thing as our denominator, so we get that denominator, the square root in there to cancel. So I've got root x over root x, and then if I multiply up top, that just turns into 2 root x. So we could do something like this again. We could throw in some numbers. So this example is not on your paper. I'm just going to make this one up. Let's say we have x over the square root of 17, right? And so the problem here is the root 17 in the denominator. So to simplify that, I'm going to multiply by root 17 over root 17. Okay, so the same radical in the numerator and the denominator. So in the denominator, a root 17 times a root 17 is just 17. And then up top, we'll just have x root 17. Alright, so you multiply by the same thing as the radical in your denominator, and you do that for top and bottom, so that way you're just multiplying by 1. So the next example is something, well, what if we have a cube root? So for the second one, I have 3x over the cube root of 4x, okay? So if we're going to multiply by the cube root of 4x, well, it's a cube root. When you have a cube root, you need 3 of those to cancel. And so if we already have 1, then that means we need 2 more. So I'll have 2 more of these. Right, so 1 cube root, 2 cube roots, 3 cube roots. when you have 3 cube roots, the cube root canceled, and you're left with just 4x. Okay, so we multiply by the same thing in our numerator, so that'll be cube root of 4x times the cube root of 4x. Okay, so up top, well, we have our 3x on the outside, and then if we have 2 of these, well, then that's going to be the same thing as, let's see, I can do 4 times 4, which is 16, and then x times x, which is x squared. Now, there is some simplifying here that we can do. We've got to evaluate that cube root of 16. So 16, we can break that into 8 times 2, and then we still have that x squared on the inside, okay? And then this is all over 4x. So, the cube root of 8 is 2, so we already have our 3x on the outside. If the cube root of 8 is 2, we'll pull that out. And then this 2 on the inside, we can't take the cube root of that, so we have to leave that in. And then our x squared, we'll also leave that on the inside. And then this is all over 4x. Alright, so 3x times 2, we'll get 6x. And then this is the cube root of 2x squared all over 4x. And then we can simplify between the 6x and the 4x. So these x's will cancel. This 6 we can divide by 2, and that turns into 3. This 4 we can divide by 2, and that turns into 2. So what we end up getting for our final answer is 3 times the cube root of 2x squared all over 2. And it's as simple and as nice as you can make it. Okay. Let's do another cube root example. Let's see. What if we have something like 5 over the cube root of 10? Okay? 5 over the cube root of 10. So, we have 1 cube root of 10 in the denominator, so we need 2 more. So I'll have cube root of 10, cube root of 10, and then I'll have the same thing up top, 2 cube roots of 10. Alright, now, down below, so multiplying out 3 cube roots of 10, that's just going to turn into 10. And then up top, we'll have 5 times the cube root of 100, and I don't think we can simplify the cube root of 100. No, we can't. That's as far as that can go. But what we can do, well, actually, no, it's not as far as we can go. One last step is we could simplify between the 5 and the 10, right? So this 5 and this 10, we could divide both of those by 5, so the 10 would turn into 2, the 5 would turn into 1, and so then our answer is the cube root of 100 over 2. Okay, so there's another cube root for you. The last kind of division that we have to talk about is multiplying fractions that have things being added or subtracted to other things. So, in the previous examples that we did so far today, everything in our numerators and denominators was being multiplied, so that was all nice and easy to handle. But we could have something like one of the examples that you have, 2 minus the square root of 5 over 3 plus the square root of 2. Okay? So, you can see in our denominator, these things are being added to each other. So this is going to require a different process. So what we can do is we're going to multiply by the complex conjugate. Okay? So that'll be 3 minus root 2 down below, and then 3 minus root 2 up top. And so what we'll have to do in the numerator is we'll FOIL. Alright, so if I multiply my first, 2 times 3 is 6. My outers, that'll give me negative 2 root 2. My inners, that'll be negative 3 root 5. And then my last, that'll be negative root 10. Okay, now, in our denominator, we can multiply that. We could FOIL if you wanted, or you can use the shortcut. So remember, the shortcut for multiplying complex conjugates, or rather conjugates I should say, is your first squared minus your last squared. So the first one we have here is 3. So we'll square that, and then actually I should do this down here. And then minus, and then my last is root 2, right? And then we square that. Okay, so 3 squared is 9, and then root 2 squared is 4. And 9 minus 4 is the same thing as 5. So your new denominator is 5. So now what we can do is we can simplify our numerator, combine like terms. So let's see. Well, so the only terms that I could combine are what we have here in the middle. So then actually, no, nothing can be combined because all of these roots are different and none of them can be simplified. Yeah, so your answer is just what you have. So 6 minus 2 root 2 minus 3 root 5 minus root 10. None of those can be simplified. All over 5. And that's it, and you're all done. Okay, so let's take a look at the second example. So for the second example, we have root 3 plus root y over root 3 minus root y. Okay, so we multiply by the conjugate of this. So the conjugate of our denominator, which is going to be root 3 plus root y over root 3 plus root y. So this is the exact same thing as your denominator, except you flip the sign. Okay? So, and it just so happens, it doesn't always work out this way, but it just so happens this is a coincidence in this particular problem that it's the same thing as the numerator. Okay, it doesn't always work out that way, just a coincidence here. So up top, we're going to have to FOIL, right, so you can picture that happening. So if I do, so my firsts, I'll have root 3 times root 3, my outers plus root 3y, my inners is plus root 3y, and then my last is plus root y, root y. Okay, and then this is all over, so we can use our shortcut again. So we'll do first squared minus last squared, so that's going to be root 3 the whole thing squared minus root y the whole thing squared, so that's going to be 3 minus y. And so that's our denominator here. So then what we have to do, we've got to simplify that numerator. We can definitely clean things up. Okay, so root 3 times root 3 is 3. We have a root 3y plus another root 3y. That's going to be 2 root 3y. And then root y times root y is y. And so this is all over 3 minus y. And that is as far as you can go. And you're all done. So that's the end of 724. Well, at least the first day of it. So I hope you know enough to try out the first homework assignment. And then tomorrow we'll do some more practice in all of these areas. And then you'll have another homework assignment to practice these things.